Well, hello, Dr. Kowalczyk, and anybody else that gets to see this. For my creative contribution, I've decided to create a walkthrough for solving one of the summative problems. This question comes from summative problem set number 1, and it's question 2. Question reads as follows. The work function of metallic rubidium is 2.09 electron volts. We have two light sources, one with wavelength 550 nanometers, another with wavelength 200 nanometers. And we are asked to determine which of these light sources is capable of ejecting electrons from the surface of rubidium via the photoelectric effect. And then for the light sources that will eject electrons, to calculate the kinetic energy and the speed of the electrons. So we're given that the work function of metallic rubidium is 2.09 electron volts, so we can write that down. Uppercase phi, which is the work function, is equal to 2.09 electron volts. We also know that the work function is equal to h, which is Planck's constant, multiplied by the initial velocity, v naught. And v naught can be simplified because we are looking for, because we're trying to determine the light sources that are capable of ejecting electrons via the photoelectric effect, we're going to want to look for the initial wavelength of the metallic rubidium, whose work function is 2.09 electron volts. So this can simplify down to Planck's constant times the speed of light divided by initial wavelength, which is what we are looking for. So we can simplify that down to wavelength equal to Planck's constant times the speed of light divided by the work function. And we know that Planck's constant is 6.626 times 10 to the negative 34 joule seconds. And we know that the speed of light is 3 times 10 to the 8 meters per second. And the work function is given in electron volts. And in order for the units to cancel out, we are going to want to multiply that to convert electron volts into joules. We're going to multiply by 1.602 times 10 to the negative 19 joules per electron volt. This is a conversion factor. And this will give us our initial wavelength, which is equal to 5.94 times 10 to the negative 7 meters. And because it's a wavelength, we want to look for nanometers. So because we're looking at a wavelength, we want this value to be in nanometers. Multiplying this value by 1 times 10 to the negative 9 nanometers will give us 500 and 94 nanometers. So we have just found the threshold wavelength. I'm sorry, I've been saying initial wavelength. It's the threshold wavelength to be 594 nanometers. And any wavelength of light lower than this threshold wavelength will emit electrons. And because we're given that the two light sources we're looking at emit at wavelengths of 550 nanometers and 200 nanometers, we know that both light sources are capable of ejecting electrons from the surface of rubidium. So for the next portion of this problem, we're going to start a new page. We're asked to calculate the kinetic energy and speed of the ejected electrons. So we're looking for kinetic energy and speed. We know that kinetic energy in terms of work function and wavelength can be solved using this equation. We're going to take Planck's constant times the speed of light divided by wavelength minus the value of the work function and we can find velocity or speed by using a function that involves the kinetic energy, which we will first be solving for. So kinetic energy, an equation for kinetic energy can also be written as 1/2, if we remember back to general physics, 1/2 mass times velocity squared, this involving velocity. So we can isolate velocity to one side of the function, velocity squared is equal to 2 times the kinetic energy divided by mass. And we can square velocity, both sides of the function, to get velocity equals the square root of 2ke divided by mass. So right up there. And we can use both of these functions to solve for the latter half of the problem. Okay, so I have the equations that we're going to need written nicely in this little bubble. Well, not so nicely. Please forgive me. This is my first time using a drawing pad, and I'm going to get rid of all of this information. Okay, let's begin with the light source at a wavelength of 550 nanometers. So a few bits of information that we should know before we get into these equations. We know that the mass, which is a part of the speed function, the mass of an electron, is given as 9.11 times 10 to the negative 31 kilograms. And we also know that the value of the work function in joules is going to be the same for both sources of light. It's going to be 2.09 electron volts times that conversion factor of 1.602 times 10 to the negative 19 joules per electron volt, which is equal to 3.35 times 10 to the negative 19 joules. Okay, so we're going to solve for kinetic energy. Kinetic energy is equal to Planck's constant, 6.626, times 10 to the negative 34 joule seconds, times the speed of light, which is 3 times 10 to the 8 meters per second, divided by the wavelength we are looking at, 550 nanometers, minus the work function, which is the same for all wavelengths of light coming off the metallic rubidium. So that's equal to 3.35 times 10 to the negative 19 joules. This in joules gives us a kinetic energy of 2.66 times 10 to the negative 20 joules. We also need the answer in electron volts to solve for the speed after this equation, and that is equal to 0.17 electron volts. Okay. So now calculating for speed. equal to the square root of 2 times the kinetic energy in electron volts, 0.17 electron volts, divided by the mass of the electron, equal to 9.11 times 10 to the negative 31 kilograms. And that gives a value of 2.42 times 10 to the 5 meters per second. These are the answers for part 2 of the question for a wavelength of 550 nanometers. So now we can move on to the wavelength at 200 nanometers. Okay, so I've taken the liberty of copying all the pertinent information from that page onto a new one. So we're looking at the light source at 200 nanometers. We can calculate the kinetic energy, again, as Planck's constant, 6.26 times 10 to the negative 34 joule seconds, multiplied by the speed of light, 3 times 10 to the 8 meters per second, divided by the wavelength that we are looking at, 200 nanometers, minus the work function, the same work function in the last portion of the question, 3.35 times 10 to the negative 19 joules. And that gives us a kinetic energy of 6.59 times 10 to the negative 19 joules, or a kinetic energy in electron volts of 4.11. We're going to use the electron volt unit of the kinetic energy to solve for speed. Speed is equal to 2 times the kinetic energy divided by the mass of the electron, same as in the last question. 9.11 times 10 to the negative 31, kilograms. And that gives us a speed equal to 1.20 times 10 to the 6 meters per second. So there's the speed, and there's the kinetic energy for the light source at a wavelength of 200 nanometers. Both the kinetic energy and the speed of the electron from the light source at 200 nanometers are faster than the electron's kinetic energy and speed from the light source at 550 nanometers. Looking at the function for kinetic energy, you can see that it's logical. All values are constant except for the wavelength. A smaller wavelength in the denominator will give a larger value, and a larger value in the kinetic energy creates a larger speed. If you also look at that function in the numerator, if the kinetic energy is larger, then the speed will be larger. So it's interesting to know the kinetic energy and speed of ejected electrons from light sources. When electrons get excited and therefore ejected, they emit light. This kind of information can be important in photoelectric science. I don't know, maybe if you're developing like light bulbs or something, neon signs. Yeah. Well, yeah, thank you for sticking around. Thank you for listening. I hope that my work was straightforward, and I hope my handwriting wasn't too bad. All right, signing off. Thank you.